Every year, over 9 million tons of copper scrap are recycled worldwide. That's enough to build 1,800 statues of liberty. But where do old cables, transformers, and copper wires go after disposal? What do they do with them in the heart of factories where temperatures exceed 2,000 degrees Fahrenheit? And why can recycling 1 pound of copper save as much energy as a whole house needs? If you watch until the end, you'll learn a secret you've never heard before. So, in what city did you last see a copper factory? Write it in the comments. It's interesting to check the geography. It all starts at the huge warehouses of recycling plants. Thousands of pounds of various copper scrap flock here. Thick power cables from industrial sites lie next to thin wires from household appliances. Old transformers are neighbors with remnants of construction wiring. Each element has its own story, but they all share one thing. They are ready for a new life. The first stage of recycling is careful sorting. Experienced specialists separate the scrap by type and degree of contamination. Clean copper wire is separated from insulated cables. Thick industrial cables are separated from thin household wires. This is a critically important step, as different types of scrap require different approaches to recycling. The next stage is mechanical cleaning, a true art of modern technology. Powerful shredding machines cut the cables into fragments 2 or 3 inches long. Special separators use the difference in material density, as copper is heavier than plastic and rubber, making it easy to separate. Vibrating tables and air currents finally clean the copper fragments of insulation remnants. The output is relatively clean copper pieces, but this is just the beginning. The real magic begins in the melting shop. Huge induction furnaces heat the copper to a temperature of over 1,984 degrees Fahrenheit, the melting point of copper. The metal fragments gradually turn into a red-hot, almost golden liquid. This sight is always impressive. Hard, cold pieces of metal become a living, pulsating mass. But temperature is just a tool. The main action happens at the molecular level. During melting, impurities behave differently. Some float to the surface as slag, others dissolve. Master metallurgists carefully control the process, skimming off the slag and adding special substances called fluxes, which help remove unwanted elements. The first refining is complete, but this is not the end. The molten copper is poured into special baths for electrolytic purification. This is the most precise stage of the entire process. An electric current of several thousand volts is passed through the melt. Under its influence, residual impurities, iron, nickel, zinc, lead, migrate to the electrodes and are removed from the melt. Electrolysis lasts for several hours. The temperature is strictly controlled between 2,100 and 2,200 degrees Fahrenheit, and the current strength is regulated with an accuracy of tenths of an ampere. Laboratory analyses are conducted every 30 minutes. Chemists check the metal's composition, tracking how the amount of impurities decreases. Gradually, the purity of the copper increases. 95%, 97, 98, 99. And finally, the coveted mark of 99.9% is reached. The purified copper is ready for forming. The molten metal is poured into special molds, ingot molds. The molds are preheated to a temperature of about 1,800 degrees Fahrenheit to avoid thermal shock. Slow, controlled cooling allows the copper to crystallize with the correct structure. Perfectly uniform ingots weighing from 50 to 100 pounds or cylindrical billets 6 or 8 inches in diameter are formed. These billets are the basis for future cables. They go to the wire drawing shop where the next transformation takes place. A wire drawing machine is a series of successively arranged dies, openings of different diameters. The billet passes through the first opening, about 3 inches in diameter, then through a smaller one of 2 inches, then 1.5 inches. With each pass, the diameter decreases and the length increases. The drawing process requires enormous effort. Powerful electric motors with up to 500 horsepower pull the copper through the dies with a force of tens of tons. The metal deforms but does not break because copper is plastic and can withstand such a load. Gradually, the thick billet turns into a thin, flexible wire with a diameter from ½ an inch to even thinner. Each stage of drawing is strictly controlled. The diameter is measured by laser devices. The feed speed can reach 100 feet per minute and is automatically regulated. If defects appear, such as scratches, irregularities, or cracks, the process is stopped for correction. The finished wire undergoes a final quality control. Not only the geometry is checked, but also the electrical properties. The resistance must not exceed a certain value per 1,000 feet of length. Conductivity, mechanical tensile strength. All parameters must comply with strict American Society for Testing and Materials standards. After all, this wire will become the basis for cables that will transmit electricity to homes, offices, and factories. The final stage is the manufacturing of the finished cable. Copper wires are covered with insulation up to 1/10 of an inch thick, polyethylene, polyvinyl chloride, or other modern materials. Depending on the purpose, the wires can be twisted into the required configuration. Power cables for 120 or 240 volts, information cables of category 5 or 6, special purpose cables, each has its unique design. Packaging the finished product is the final touch. Cables are neatly wound onto spools, 3 or 4 feet in diameter, or placed in boxes of standard sizes. Each unit is marked, indicating the length in feet, the cross-section in American wire gauge, and technical specifications. Underwriters' laboratory certificates confirm that the product meets all American safety standards. The result of this complex technological symphony is impressive. From scrap that seemed like useless junk, high-quality cable is born. It is ready to serve for 25 or 30 years, providing reliable transmission of electrical energy from residential buildings to large industrial complexes. But this is not just a technological process. It is a philosophy of sustainable development in action. Every ton of recycled copper is a ton that does not have to be mined from the Earth's depths. It means conserved natural resources, less environmental impact, and a cleaner environment for future generations. Recycling 1 ton of copper saves about 2.5 tons of ore. The cycle is complete, but it is endless. When, decades from now, this new cable becomes obsolete again, it will return here to begin a new journey of transformation. Copper is the metal of eternity, which can be recycled an infinite number of times without loss of quality. And in this lies its true value. The production figures are staggering. Over 9 million tons of copper scrap are recycled annually worldwide. This is equivalent to the weight of 1,800 statues of liberty. In America, the average family uses about 280 pounds of copper in their home, from electrical wiring to plumbing pipes. 1 million pounds of recycled copper saves enough energy to power 1,000 homes for a year. This is 85% less energy than is needed to mine new copper from ore. Recycling also reduces carbon dioxide emissions by 65% compared to primary production. The largest amount of copper scrap comes from the construction industry. That's 31%, from electronics 21%, and from the automotive industry 12%. 1 pound of copper wire can be drawn to a length sufficient to wrap around a football field 23 times. Modern factories can process up to 400 tons of copper scrap per day, producing wire with a total length of over 50,000 miles. Over the last decade, the price of copper scrap has increased by 180%, making its recycling extremely profitable. Today, recycling provides 40% of the world's copper needs, and this figure continues to grow. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is billet, stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining crudestis, precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Karblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing. It's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string. Those are steel pipes with a cutting bit on the end. Bores into the earth, spinning it up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins. Actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, Let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. One barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet, and that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length. A groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a 45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection. By eye, through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. Imagine this: red-hot metal up to 33 feet long, bending as easily as if it were a sheet of paper. Every year, factories all over the world create millions of parts, from car bodies to giant pipes, thanks to bending machines. But how are perfect bends, channels, and even spiral shapes for oil and gas giants born from cold, formless steel? And how can it be done without wasting tons of energy? Let's dive into a world where metal obeys human will. A bending machine. Think of it like a big construction set for metal. Imagine a flat sheet that needs to be bent into a specific shape. The machine takes this sheet and bends it using special tools to get the desired angle or form. First things first, the metal sheet needs to be checked to make sure it's suitable for the required part. This includes checking dimensions and looking for defects like cracks or breaks. The metal sheet is cleaned of dirt and rust using a wire brush or sandpaper. This is necessary to ensure clear marking and subsequent processing. Markings are applied to the sheet using special tools like rulers, squares, and scribers. The layout includes drawing center lines and contour lines, as well as marking the centers for any future holes in the part. To make sure the markings are clear and don't rub off during processing, the metal surface is coated with a special paint. Dry chalk, a chalk solution with glue, or a copper sulfate solution might be used. After applying the markings, they are checked against the part drawing. In large industrial settings, automated systems are often used to lift and place metal sheets onto the machine. These systems might include conveyor lines and robotic arms that precisely position the metal sheet on the machine's bottom die. In smaller workshops, or during small batch production, metal sheets might be placed manually by workers. Workers in protective suits and gloves lift the sheets using special tools or lifting equipment and place them onto the machine. Metal sheets can vary greatly in size, from small ones easily lifted by hand to enormous ones requiring special lifting equipment. In large industrial settings, you might see sheets up to 33 feet long and up to 10 feet wide. Then, the necessary tools are selected: a punch for the upper part and a die for the lower part. These determine exactly how the metal will bend. During the sheet metal bending process, the machine presses the punch onto the sheet and it bends into the die, forming the required shape. This process allows for creating various shapes and angles, depending on the type of punch and die used. The most common method is V-bending, which is used to create angles of various degrees. This shape is widely used in manufacturing elements for construction, machine, and equipment housings, frames, and so forth. U-bending is used to create U-shaped channels from steel and other metals. This shape is ideal for manufacturing metal profiles and channels. Radius bending is used to make parts with cylindrical or conical configurations. Such shapes are used in the production of pipes, cylinders, and other three-dimensional structures. One variation of polygonal bending used to obtain complex shapes is P-bending. Bending sheet metal allows for creating various shapes and angles, but creating a spiral shape is a more complex process. Spiral forms are usually made using special methods and equipment, such as roll-forming machines. These machines are used to produce cylindrical, conical, and other curved surfaces. They allow for creating spiral shapes by sequentially passing the metal through rollers that gradually form the desired shape. Such machines are widely used in the production of pipes, cylinders, and other metal structures that require a spiral form. While roll-forming machines are operating, you can see how metal sheets pass through the rollers, gradually acquiring the desired spiral shape. Spiral forms are used in various industries and everyday applications. They offer high strength, excellent conductivity, resistance to corrosion, and fatigue. Springs, connectors, heat exchangers, electrical engineering and electronics, the oil and gas industry, chemical processing, and medical instruments all use products with spiral shapes. For example, in beryllium copper spiral tubing, the spiral form is used in 50% of applications due to its high conductivity and strength. Spiral cables are used in over 70% of industrial automation systems because of their flexibility and resistance to mechanical wear. Spiral springs are found in over 30% of mechanical drives due to their ability to provide varying spring forces. Spiral pipes, often referred to as coiled tubing, offer several advantages in the oil and gas industry. They can easily adapt to changes in elevation and direction during the transport of oil and gas. This is particularly important when constructing pipelines in complex geological conditions. Coiled tubing has a spiral seam, which facilitates installation. This can reduce assembly time compared to traditional pipes with straight seams. Coiled tubing is used in well clean-out technology after hydraulic fracturing. Nitrogen is pumped through these tubes to wash out proppant from fractures, which increases maintenance intervals and reduces the time needed to bring the well back into operation. Metal forms can be made from various materials, such as steel, aluminum, or copper. The choice of material depends on the requirements for the product and the possibility of reuse or recycling. Traditional manufacturing methods can involve high energy and resource consumption, which can negatively impact the environment. However, modern technologies, like using renewable energy sources and optimizing production processes, can significantly reduce this impact. Metal forms can be recycled and reused, which reduces waste and the need for virgin materials. This is especially important for steel and aluminum products. To protect metal structures from corrosion, powder coatings are often used. These are more environmentally friendly compared to traditional paints because they do not contain organic solvents or harmful substances. Switching to solar, wind, or hydropower can reduce greenhouse gas emissions by 70 or even 90% compared to traditional energy sources. Improving technological processes and automation can reduce energy consumption by 20 or 30% and cut waste by 25%. Reusing metal forms reduces waste by 50 or even 70%. Imagine a bearing, larger than a passenger car, that operates without service for 100,000 hours and turns a 5-megawatt wind turbine. Its balls are polished to a precision of 4/millionths of an inch. The melting point of the steel used is almost 3,000 degrees Fahrenheit. Manufacturing it requires factories the size of cities, cranes that lift railroad cars, and presses that squeeze metal like modeling clay. But that's just the beginning. What you are about to see isn't just production. This is industrial magic that holds the whole world together. Where does a giant industrial bearing begin? Not with a blueprint, not even with a machine tool. It all starts with metal. But not just any metal. Special grades of steel are used for bearings, and their chemical formulas are sometimes guarded as trade secrets. Most often, it's chromium or alloy steel with enhanced strength, resistant to extreme pressure, vibrations, friction, water, and even time. The ore from which the steel is smelted arrives from different corners of the globe. It's often extracted through open pit mining, from enormous quarries where dump trucks have wheels as tall as a 2-story house. Then, the ore is delivered to metallurgical plants. These are cities in miniature that operate without sleep or weekends. In blast furnaces, the ore is melted at temperatures close to 3,000 degrees Fahrenheit. Alloying elements like chromium, manganese, and molybdenum are added, and the molten steel is poured into molds, creating large steel ingots. But this isn't a bearing yet. It's just raw material. Next, the ingots are cut into pieces, rolled, heat-treated, and transformed into so-called rings, blanks from which the bearing will eventually be machined. They are transported by special trailers or by rail to machine building plants. A single blank can weigh a ton, and moving it requires a crane. Precision and quality start right here. Any crack, dent, or internal inconsistency, and the entire batch can be rejected. That's why materials undergo rigorous inspection at the factory: visual, ultrasonic, and magnetic particle inspection. The production of a giant bearing forgives no mistakes. Everything must be nearly perfect. Such giant industrial bearings, larger than a passenger car and weighing over 3 tons, are used in heavy-duty equipment. For example, in wind turbines. In the mining industry, huge bearings rotate in crushers, mills, and mining conveyors. In metallurgy, they are used in rolling mills and blast furnaces. Offshore platforms and ships, cement plants, hydroelectric power stations, oil extraction, all require extra-large, super strong bearings. After all, they withstand extreme loads, rotate with immense force, and operate in aggressive environments where smaller parts simply wouldn't survive. After the metallurgical plants deliver the steel ingots, each weighing tens of tons, to the bearing manufacturing facility, the magic begins. These ingots don't have any shape yet, but they already conceal future strength. Giant cranes lift them. One such hoist can support the weight of a railroad car, and with precision down to the inch, lowers the red-hot blank to where they will start sculpting the bearing from it. The scene looks like something from a science fiction movie. Massive hydraulic presses with thousands of tons of force squeeze the metal like modeling clay. It's rolled, pressed, heated again, and it begins to transform into a huge metal ring, rotating on a conveyor. Every movement is accompanied by roars, clangs, and hissing steam. Heating furnaces heat the steel up to 2,000 degrees Fahrenheit. That's almost twice what's needed to melt lead. Workers in protective gear look like characters from a post-apocalyptic movie, and for good reason. One spark could cause serious injury. But thanks to automation and strict safety standards, everything proceeds exactly according to plan. As soon as the ring takes shape, its machining begins. Like a giant potter's wheel, it spins on lathes that, with a screech, shave off layers of metal mere thousandths of an inch thick, grinding the surface to a perfect smoothness. There's no room for error here. Even a tiny inaccuracy can be fatal at the speeds these bearings rotate. Behind every giant bearing stands a team that knows every part of the process inside out. These are engineers, technicians, and master craftsmen who study blueprints, check temperature regimes, lubricate parts on time, and monitor precision down to the micron. Some have worked here for decades. Their hands are covered in grease, their eyes are tired but intense. And despite the noise, the risks, and the difficulty of the work, many wouldn't trade this rhythm for anything. The first massive bearings appeared in the 20th century, when industry began to grow taller and wider. Hydroelectric turbines, rotors in oil refineries, tower cranes, all needed reliable rotators for colossal loads. After grinding comes the most critical part: quality control. The giant bearing undergoes a thorough inspection, like an athlete before the Olympics. Its surface is examined for microcracks using ultrasonic sensors and magnetic particle inspection. The massive ring lies in a special bath, and waves and magnetic particles are passed over it. They'll glow in places where there's even the slightest damage. Then comes balancing. The huge metal structure is mounted on a special stand resembling giant scales. The bearing starts to rotate, slowly at first, then faster. Computers detect any imbalance, and technicians add or remove metal in the necessary places. Everything is done so that in the future, this bearing can operate at tremendous speeds without the slightest wobble. Inside an industrial bearing are steel balls or rollers. Each ball starts as a small metal cylinder, a wire rod, about 1/2 inch to 2 inches in diameter. It's cut into blanks, and then cold heading is used to form the future ball, still with noticeable seams and roughness. At this stage, the blank weighs from 1/10 of a pound to 1.5 pounds, depending on the size. These blanks are called flashes. Next is the tumbling process, where the blanks are passed between two discs spinning at incredible speeds, up to 1,800 revolutions per minute. This removes the seams and achieves a more perfect shape. Then comes heat treatment at 1,500 degrees Fahrenheit to give the steel strength, and only after that, the finest grinding. The balls are ground on high-precision machines, with a tolerance no greater than 4/millionths of an inch. Polishing takes 48 hours, and the final result is a ball that can rotate millions of times without wear. A similar process applies to rollers. They are machined from high-strength steel, can be up to 8 inches long, and withstand loads over 10,000 pounds per square inch. They are also ground, heat-treated, and each undergoes individual geometry checks. After manufacturing the rolling elements, it's time for assembly. Between the outer and inner ring of the bearing, a separator is installed, a special cage that evenly spaces the balls or rollers. Separators can be steel, brass, or polymer, depending on the application. For instance, polyamide cages are often used in wind turbines due to their moisture resistance. A typical bearing for a 5 megawatt turbine might contain around 70 balls with a diameter of 2.5 inches, or 30 rollers 6 inches long. In the final stage, the assembly is lubricated, using grease with an operating temperature range from -40 degrees Fahrenheit to +400 degrees Fahrenheit. Seals or protective shields are added, and the bearing is ready for work, designed to last 100,000 hours without service. Global leaders in bearing production manufacture enormous volumes. For example, the Swedish company SKF produces 600 million bearings annually. The Japanese company NSK produces approximately 1,250,000 bearings per year. The main challenges facing the bearing industry relate to the high demands on materials and technologies, the need for strict quality control, and the constant implementation of innovations to maintain competitiveness. Fluctuations in global raw material prices, competition in the global market, as well as the need to improve energy efficiency and reduce production costs create additional difficulties for companies in the sector. Every year, thousands of steel frame structures are built on construction sites around the world, not for small homes, but for skyscrapers, bridges, factories, and sports arenas. Today's steel fabrication plants are not just about machines and metal. They are high-tech hubs where heavy-duty equipment pushes its limits. You will find cranes lifting hundreds of tons, robots performing precision welds, and advanced computer systems overseeing quality control. So, how are these structures made? How does the heavy machinery work, and why is every step, from metal melting to final assembly, absolutely critical? You will definitely want to see this for yourself. Steel preparation is the very first and most important step in manufacturing frame structures. At steel mills and factories, the process starts with massive metal stock delivered in the form of steel sheets, rods, or blocks, some weighing up to 50,000 pounds. These materials often arrive in specialized containers that can carry multiple tons of metal, and large overhead cranes, capable of lifting up to 100 tons, are used to move them across the facility. One of the most impressive sights is the lifting and transport of these heavy chunks of metal. The crane approaches a towering pile of steel blocks, grips them using heavy-duty hooks, and with astonishing precision, hoists them to the next stage of production. Crane operators must work in perfect sync, because even a small mistake can cause major damage or a dangerous accident. The metal blocks are usually cut down using industrial shears or plasma cutters. These specialized machines can slice through steel up to 3 inches thick in just 1 second. They create precisely shaped profiles for the next phase of production, delivering perfectly clean cuts that would be nearly impossible by hand. Once the steel has been trimmed into the required shapes, it moves on to the melting stage. This is one of the most dramatic parts of the process, as the steel is heated to over 2,800 degrees Fahrenheit, producing smoke clouds and bursts of flame. Technicians operate powerful furnaces that can process up to 300,000 pounds of metal per minute. They must keep the temperature steady, because even a small fluctuation can change the steel's properties. Once liquefied, the steel is ready to be poured into molds. At every stage of this process, quality control is key. Special computer systems track temperature, pressure, and other vital data to ensure consistency and precision. When the steel reaches its molten state, the next important step is impurity removal. Impurities like sulfur, phosphorus, and other unwanted elements can weaken the metal. To eliminate these, filtration and delivery systems go into action. They use physical filters to attract unwanted particles or inject chemical agents that bind with them to form slag. The slag rises to the surface, where it can be easily skimmed off. At this point, large gas jets, usually nitrogen or oxygen, are introduced to further purify the steel. These jets are injected through special nozzles that help break down and disperse impurities. Once the steel is clean and cool, it moves to the rolling stage. The remaining molten metal is sent to rolling machines, where giant presses flatten it into long steel sheets. Each sheet goes through multiple rolling phases, with pressure reaching up to 10,000 tons per square inch. The finished sheets can be less than half an inch thick, depending on the needs of the structure. Next comes shaping the individual structural elements. CNC machines and heavy-duty tools cut and form the sheets and beams according to the blueprints. Computer-controlled systems allow for cuts accurate down to the millimeter. Individual elements, like beams, columns, and joints, are shaped and prepared for welding. A single machine can produce up to 500 components per day. Welding and assembly are some of the most impressive parts of building a steel frame. After the metal parts are cut and prepped, they are positioned and joined using arc welding, gas welding, or even laser welding. Heavy metal segments, weighing over 500,000 pounds each, are hoisted by cranes capable of lifting 50 to 100 tons. These cranes maneuver the sections into place using steel cables and counterweights, allowing precise placement before welding. Meanwhile, welders get to work at the center of the operation. They use machines powered by electricity or gas mixtures that can reach temperatures of over 6,500 degrees. These high temperatures allow metals to bond at the molecular level. Welders carefully guide the arc or flame to melt the edges and fuse them. The seams must be flawless, so the process demands total accuracy. After welding, every seam is rigorously inspected. Laser scanners examine the joints for cracks or flaws. Ultrasound checks are also performed to detect microscopic gaps or defects inside the welds. At the same time, other crew members install additional structural elements like beams and support frames, with precision down to the millimeter. Automated robotic systems also play a huge role. These machines position steel components and hold them in place while welders work. Once everything is welded and secured, the final steps begin: grinding and painting the joints for corrosion protection. This finishes the steel frame assembly and prepares it for transport or installation on site. For large-scale projects, this process can take weeks or even months. It is not just technically complex, it is visually stunning. Watching huge steel pieces rise and come together to form new shapes is truly amazing. Structures that must endure extreme conditions undergo additional treatment, like alloying and anti-corrosion coating. This extends their lifespan and keeps them looking good for decades. Zinc coatings or special heat-resistant paints are often used. Stress testing using pressure rigs helps engineers understand how the frame will perform under load. Computer simulations reveal weak points and allow stress to be redistributed where needed. These tests often last up to 72 hours, depending on the complexity of the structure. Finished steel components are transported to the construction site using specialized trucks and carriers. Gantry cranes capable of lifting 200 tons handle these deliveries. At the site, tower cranes and mobile cranes take over, lifting each piece into position. Assembly can take days or weeks, depending on the size and complexity of the project.